Okay, welcome back, everyone. Let me just remind you. Oh, actually, first, before I do that, I'll remind you that the PSET 3 is due today, and the last question on PSET 3 is about just what do you want to do for the final project. If you have questions about this, feel free to come to my office hours and ask me, or you can email me. I can give suggestions if you're confused about like what would be a good thing to do, you know, like a good paper to read or something. And then I'll also post PSET 4 today, which I think will be easier than PSET 3. So hopefully that's true. Okay, so last time we were talking about the geometric representation of a Coxeter group. We said V is going to be a real vector space with a basis indexed by the simple reflection. So we'll call the basis elements alpha sub S for each simple reflection S. And then we defined this bilinear form by saying that alpha S bar alpha S prime should be negative cosine of pi over m of S comma S prime, where these are the numbers that you use to define your Coxeter group. From this, we can define for each simple reflection this linear map sigma sub S, which goes from V to V, and we define it by saying that sigma sub S of beta should be beta minus 2 alpha S bar beta times alpha S. I'll do examples of this today just to try to make it seem a little more clear why we're defining things with like cosines and like why this is the formula that we should want. And then I stated, and I'm not going to prove this, but I'll just say that if you have any element W in your group and you write it as a product of simple reflections, then you can define sigma sub W to be the product of the corresponding sigma things, right? Sigma sub SI1 dot dot sigma sub SIR. And this is well defined, so it doesn't depend on the way that you chose to write it as a product of simple reflection. And this doesn't even have to be reduced. I'll just point out that well defined is not hyphenated because you know, so you should write, like if I said this is a well-defined map, then you put a hyphen. But if it's just this thing is well-defined, there's no hyphen. So just a tip. Okay. So I was doing an example, and I'll go through this again. So let's say W is Sn. And remember, we were going to let V be this vector space, which is just the set of vectors gamma 1 through gamma sub n in R to the n, such that the sum, maybe I should write it down here. V is the set gamma 1 through gamma n, such that the sum is 0. Why did I write a gamma? There we go. And we're going to let EI be the ith standard basis vector. So this here is the vector with a 1 in position I. And here we're letting alpha Si, which I'm just going to call alpha I so that I don't have the double subscript. This is going to be just EI minus EI plus 1. And so in this case, these alpha sub i's actually do span this vector space. They form a basis for V. And we computed that if I take alpha I bar alpha I, we said this is going to be 1. And if I take alpha I bar alpha I plus or minus 1, this is negative a half. And alpha I bar alpha j is 0 if I and j differ by at least 2. So then sigma sub si of alpha I is just going to be alpha I minus 2 alpha I bar alpha I alpha I. So this is 1, so I'm saying it's alpha I minus 2 alpha I, so this is just negative alpha I. And this will be true in general, that whenever you have sigma sub s applied to alpha sub s, it's just going to give you negative alpha sub s. So here, sigma sub si of alpha I plus 1 is alpha I plus 1 minus 2 alpha I bar alpha I plus 1 alpha I. And this is alpha I plus 1. So this is negative a half. This is bilinear form, so we get negative 2 times negative a half, so that's just plus 1. So this is alpha I plus 1 plus alpha I, which is ei minus ei plus 2. And I pointed out that this is just the vector that you get by taking alpha sub I plus 1, which would be ei plus 1 minus ei plus 2, and you're just swapping the coordinates in positions I and I plus 1. Which, well, is also what happens if you apply si to alpha I minus 1. So this should be alpha I minus 1 minus 2 alpha I bar alpha I minus 1. Alpha I, this is alpha I plus alpha I minus 1, or maybe, and this is ei minus 1 minus ei plus 1, which is again what you get by taking alpha sub I minus 1 and swapping the ith and I plus first coordinates. Oh, and then I guess maybe I should have also mentioned that this is also what happens here. So negative alpha sub I is ei plus 1 minus ei, which is also what you get by taking alpha sub I and swapping the ith and I plus first coordinates. And then finally, if I do sigma sub si of alpha sub j for I and j differing by at least 2, this should be alpha j minus 2 alpha I bar alpha j alpha I. This is 0, so I just get alpha j. And again, this is what you get by swapping the ith and I plus first coordinates in alpha j, because the ith and I plus first coordinates in alpha j are both 0. Right, that's what, well, yeah. So, in this case, you're just going to fix alpha j. So maybe I'll just say that, sorry. So if beta is written as beta 1 through beta I minus 1, well, I'll just write it as beta 1 through beta n. So I'm writing it in this way in terms of coordinates. Then sigma I, or sigma si of beta is just what you get by swapping the ith and I plus first coordinates. And I know this because, well, I know that this is what it does to a basis of V. So, yes, Steph.
Okay, I'm gonna be honest, all these indices are like really confusing me, and like the way you've defined the cosine and the fact that they're like unit vectors on the EI kind of suggests that there's like a picture associated to this.
Yeah.
So could we just like do like S3 or something so I could like sort of see these vectors in the plane and stuff?
We'll do B2,
Okay.
which is also I2 of 4. Yeah, I'll do that. Let me just mention that in general, what this is going to do is if you apply sigma W to beta, this is just going to be beta sub W inverse of 1 through beta sub W inverse of n. So all I'm saying with this is that the standard geometric representation of the symmetric group is just acting on this vector space by permuting the coordinates in the way that you would want it to work. And you take inverses just to make sure that this is actually like a left action. So, but anyway, yeah, you're just permuting coordinates. Okay. One remark is that instead of writing a bunch of sigma sub s things or sigma sub w, let me just write w. So what I want to do is think of the action of, so I'm thinking of the sigma sub w's are giving me an action of the Coxeter group on the vector space V. So I can think of V as a W module. And if I think of it this way, it's sort of natural to think of like, it's actually just a group action. So the group is just acting on the vector space. And with this notation, I think it's reasonable to, instead of writing sigma sub W, just write W. So I will often just write W instead of sigma sub W. Okay, so here's another example, which is what Catherine was wanting. So let's do, oh, actually, no, let me not do B2. Let me do something even more complicated. Let's do I2 of 6. But still, it's a dihedral group. And here's, okay, let's see if I can draw this. Okay, so I want to let this, so this is the origin, and I want to let this vector be alpha sub S1. So, okay, I guess I'm thinking of, here the simple reflections are S1 and S2. And there's a 6 labeling the edge. Okay. So this will be alpha sub S1. And I want this vector to be alpha sub S2. And I'm setting this up with this picture because I want it to be so that when I apply, say, S1, by which I mean sigma sub S1, I want that to basically be the reflection through the hyperplane, the line, which is orthogonal to this vector alpha sub S1. So let me show you how this works. So this angle here is pi over 6. Let me use a different color. So the reason that we're like dealing with cosines and stuff is because we want this picture to work out. We want to say that like whenever you have just a rank 2 Coxeter group, we want things to have this picture. So this angle here is pi over 6. And if I look at, so I want to say, what is S1 applied to alpha sub S2? And by S1 I mean sigma sub S1. Well, this is supposed to be alpha sub S2 minus 2 alpha S2 bar alpha S1, alpha S1. And what is this? This is alpha sub S2 plus 2, so if I write the bilinear form is negative cosine of this thing. In this case, the m of S1 comma S2 is going to be 6. So the bilinear form is negative cosine of pi over 6. So here I get plus 2 cosine of pi over 6 alpha S1. And what is this? Like, how do I think of this geometrically? Well, if I look at so this is the angle pi over 6, so the cosine, if I sort of draw this right triangle here, well, I guess I'll just maybe draw it this way. This length, the length of this is 2 cosine of pi over 6 times the length of alpha S1. Maybe I'll just write it this way. The point is that I am taking alpha S1 and I want to add 2 cosine of pi over 6 times this vector, which is just going to be this vector. So I'm adding this, so I end up here. Does that make sense? I mean, maybe you have to stare at it, but this is just sort of trigonometry. And so you end up finding that this vector here is, oh, maybe I should have written this. Well, okay, let me erase this. This is S1 of alpha S2. And you can see that what I did when I applied S1 to alpha S2 is I basically just reflected this vector through the line orthogonal to alpha sub S1. So this is the line orthogonal to alpha sub S1, and I just took this and reflected it over. So that gives me S1 of alpha sub S2. So if I draw my picture this way, S1 is just acting on this vector by doing this reflection. And this is also how S1 is going to act on alpha sub S1. Right? So if I do S1 alpha S1, well, as I mentioned before, this is just going to always give me negative alpha S1, right? Because it's alpha S1 minus 2 alpha S1 bar alpha S1, alpha S1. This is always 1, so this is just going to be negative alpha S1. And so if this is alpha S1, then this is the negative of it, which is S1 applied to alpha S1. So I've taken 2 basis vectors, namely alpha S1 and alpha S2, and the linear transformation S1, so if I think of S1 as a linear transformation, namely like sigma S1, then it's acting on these 2 basis vectors by reflecting through this green line. So in fact, that's what it's going to do to the entire vector space. So S1 is basically just the reflection through that green line. And by a similar argument, S2 should act by reflecting through the line orthogonal to alpha S2. So if I filled this in even more, I could say this. So if I apply S2 to this, applying I'm a little confused. This is alpha S2. And if I apply S2, I guess I get here. Is that right? Yeah, I guess. this correct?
I think so.
Okay. For some reason I was, okay. Yeah, okay, I think that's fine. What else can I do? If I apply S1 to this, right, yeah, okay. So if I apply S1 to this, I want to reflect through the green. No, see, that doesn't make sense because the S1 should fix this vector.
Yeah.
And that's okay?
Yeah, it just does.
Okay, sure. So, okay. How do I get this one?
Oh, you have to, yeah, so you can't get them all by just starting with alpha S2 and applying reflections. In order to get that one, you need to start with alpha S1 and apply
Oh, it's
S2.
because this is even. It's
So,
because 6 is even, right?
yeah. Yeah.
Yeah, okay. I'm used to doing this for when it's 3, and I was like, why am I not getting all of them? Okay, yes, that makes sense. Okay, so these are some of the vectors. We could fill out the others as well. Anyway, yeah, so all of these vectors around here, those are going to be all of the roots in my root system. So the root system has these, however, like, you know, all of these 12 vectors that I've drawn.
What's a root system?
Oh, did I define the root system? Maybe I did not define. That's a good point. I didn't define that yet. Okay, so let me define the root system. Actually, before I define the root system, let me state a proposition. So the action of W on V preserves the bilinear form. And the proof, so what I mean by this is if you take two vectors beta and gamma in V, and then you look at like beta bar gamma, that should be the same as W beta bar W gamma if W is some element of my Coxeter group. So the way to prove this is to show that this is preserved under the action of any of the simple reflections, because if it's preserved when I apply a simple reflection, then it will be preserved when I apply any element of the Coxeter group. So what I want to do is say for any vectors beta and gamma in V, and a simple reflection S, if I look at S beta bar S gamma, oh, yeah, I'm not going to write parentheses around the roots, because I'm thinking of this is like a, I'm thinking of V as a W module, and so in this way it's, I guess, natural to not write parentheses. So we have this is equal to beta minus 2 alpha S bar beta alpha S bar gamma minus 2 alpha S bar gamma alpha S. So all I've done is just applied the formula for S, which is really sigma sub S. Okay? And now, because this is a bilinear form, I can expand it out with bilinearity and say that this should be, well, I take beta bar gamma and then I'm going to have minus 2 alpha S bar gamma times beta bar alpha S. That's what I get by looking at this term with this term, right? If I take beta bar negative 2 alpha S bar gamma alpha S, it becomes this. And then if I take these two terms, this should give me -2 alpha S bar beta times alpha S bar gamma. And then I want to combine, or I want to look at the last two terms. So -2 this thing alpha S, and then -2 this thing alpha S should give me +4. So I should get +4 alpha S bar beta from here, and then alpha S bar gamma from here, and then I should get alpha S bar alpha X. Okay. And I claim that this is equal to beta bar gamma, which is what I want to show. Right, so I'm trying to show that the action of S preserves the bilinear form, so I want to show that S beta bar S gamma is the same as beta bar gamma. And why is this true? This is because beta bar alpha S, well, okay, this is the same as alpha S bar beta. Right, so the bilinear form is symmetric. Just that's because im of S comma S prime is the same as im of S prime comma S. So that implies that this bilinear form that we've defined is actually symmetric. So like beta bar gamma is the same as gamma bar beta. So we have this, and we know that alpha S bar alpha S is just 1. Right, so if I plug in 1 here, then I have like -2 alpha S bar gamma beta bar alpha S, and then this is like -2 alpha S bar gamma. This is also beta bar alpha S, and then I'm adding, so I've subtracted 2 of this thing, -2 of this thing, and then +4 of the same thing. So this all cancels and we just get left with this. Does that make sense? Okay. So now I'll define the root system. So we're going to let phi be the set of vectors of the form W alpha S, where W is in the Coxeter group capital W, and S is a simple reflection. So the point is that I started with this basis, these vectors alpha sub S, and now I'm looking at just all of the orbit, the whole orbit of this set of vectors under the action of the entire Coxeter group. So in this example, what I was saying is I start with alpha S1 and alpha S2, and if I repeatedly apply S1s and S2 to these two vectors, I'll be able to generate all of these 12 vectors that I've drawn around here. So those 12 vectors form the root system. Okay, so phi is called a root system. And phi is the root system of W, and elements of phi are called roots. Oh, and I'll also say that the vectors that we started with, the alpha sub s's, those are called simple roots. The vectors alpha sub s for S and S are called simple roots. so here's a fact about the root system. So every root, beta, in phi can be written uniquely as a linear combination, let's say sum over S in S of, let's say some coefficient C sub S times alpha sub S. So this is for some real numbers C sub S. So far this is not saying anything super profound because I defined the vector space V to be a vector space without the alpha sub s's as a basis. So of course any vector, like this isn't special to just the roots, any vector can be written uniquely as a linear combination of the basis elements. But the thing that's special here is, moreover, the coefficients C sub S are either all non-negative or all non-positive.
How do you feel about hyphenating non-negative and non-positive?
I do not hyphenate them.
I also think that's
Okay, sure. Mitchell, what do you think? Okay. Okay. So let me illustrate what's going on here in this picture. If I take this vector, so actually let me draw another line in this picture. Say a yellow line. So I'm going to draw this yellow line kind of so that it's on this side of alpha S1 and alpha S2. And if I take one of my roots that's on this side of the yellow line, then I can write it as a non-negative linear combination of alpha S1 and alpha S2. So like this vector, you can see is in the non-negative span of alpha S1 and alpha S2, whereas all of the vectors over on this side are in the non-positive span of alpha S1 and alpha S2. So we'll say that a root is positive. So a root is positive if it is in the non-negative real span, or let me write it as span sub r greater than or equal to 0. So this is the non-negative span of the alpha sub s's. And then we'll say it's negative if it's in the non-positive span. So span sub r sub less than or equal to 0 of the alpha s's. So in this picture, these roots over here would be the positive roots, and these would be the negative roots. I'm going to write phi plus for the set of positive roots, and I'll write phi minus for the set of negative roots. So let phi plus and phi minus be the set of positive roots and the set of negative roots respectively. Then, well, what you can see from there, which I guess this is not hard to see, is that the negative roots are just the negatives of the positive roots. Which I'll write like that. And also, according to this fact, every root is either positive or negative or both. So I can say that the entire root system phi is just phi plus disjoint union phi minus. And, okay, so since we showed over here that the action of W preserves the bilinear form, this tells us that, well, okay, remember when we take, so actually, okay, let me write this down. Since the action of W preserves this bilinear form, and we know that when we take alpha s bar alpha s, we get 1. This is for all s and s. This implies that we have actually beta bar beta equals 1 for all roots beta. Right, this is just because to be a root means that it's of the form W alpha S for some W and W and some S and S. So this is just W alpha S bar W alpha S. But since W preserves the bilinear form, that's the same as alpha S bar alpha S, which is 1. And so one thing this implies is that if I take the set of scalar multiples of a root beta, so let's say beta is a root, and I look at all of the scalar multiples of this that are also roots, this should just be plus or minus beta. This is because, like, I know that, for example, 2 beta is not going to be a root, because if it was, then 2 beta bar 2 beta would be like 4 beta bar beta, which would be 4, but then that would say that I have a root where like that root bar itself is 4, and that's not the case. Yes, Kat?
Sorry about asking another question,
Mhm.
but is the set of roots finite or not?
Oh, good question. So the set of roots will be finite if and only if the group is finite. So for a finite Coxeter group, yes. Otherwise, no. Any other questions? Okay. I'll do an example in a second, but maybe first let me define one more thing, or 2 more things maybe. So we're going to let V star be the dual space of V. So remember what this means is that it's the set of linear functionals from V to the real number. So recall that V star is the set, or I should say the space, of linear functionals P from V to R. I mean, a linear functional is just going to be a linear map from V to R. And there is a natural pairing of V star and V, and it's defined by just saying if I want to pair a linear functional P with a vector beta, I just take P of beta. So now, if I have a vector beta in V, I'm going to consider this hyperplane which I'll call H beta. And this is the hyperplane in the dual space. It's the set of all P in V star such that P of beta is 0. Okay? And the Coxeter, yes, you have a question?
Oh, no, it's just.
Oh, okay. The Coxeter arrangement. So everything is called Coxeter something. The Coxeter arrangement of W is the set of all of these hyperplanes for various roots, like indexed by the roots. So it's the set of all, I'll call it like script HW. So script HW is the set of all hyperplanes H beta such that beta is in the root system. So let's do an example of this. Maybe I'll start with S3. So in this case, remember, we're going to let V be the set of vectors gamma 1, gamma 2, gamma 3 in R3 such that the sum of the entries is 0. And so the picture, well, if I draw something like what I had here for I2 of 6, except now this is actually I2 of 3, it's going to look like this. Something like that. maybe that's not perfect. These should be, yeah, okay, that. I want these to be 60-degree angles. This shouldn't be that hard. Okay, probably that's fine. So let's say this maybe is my alpha 1, which is actually E1 minus E2. And this is my alpha 2, which is E2 minus E3. And if I take the sum of these, so I should get this vector here, well, that's just going to be E1 minus E2 plus E2 minus E3 is E1 minus E3. And then I have the negatives of these, so this will be E2 minus E1. This is E3 minus E2. And this up here is E3 minus E1. Maybe I'll color these just to distinguish them. So here are the positive roots in orange. And the negative roots will be in green. And now I can draw, well, okay, so this is living in the space V. The dual space is a different space, but I'm going to kind of superimpose them so that I can draw the Coxeter arrangement in this space as well. But like, you should really, I guess, understand that these are actually living in different spaces, but it's kind of convenient to draw them on top of each other. Yes?
Can you label some of the vectors with like S1, S2?
Oh, yeah, I can do that. So this is equal to alpha 1, or alpha S1. This is alpha 2. This is alpha 1 plus alpha 2. And these are the negatives of them. So like negative alpha 1, negative alpha 2, negative alpha 1 minus alpha 2. Okay? So if I sort of imagine superimposing the dual space on top of this picture, then the hyperplane H beta should sort of be drawn orthogonal to beta. So the picture should look, where's the picture? The picture should look like this. So this hyperplane, which is a line, is H sub E1 minus E3. Notice that it's also H sub E3 minus E1. In other words, like the hyperplane orthogonal to the root is also the hyperplane orthogonal to the negative of the root. So here, I'll have a hyperplane like this. This will be H sub, so it's orthogonal to E2 minus E3. But it's also H sub E3 minus E2. And here I have the hyperplane orthogonal to E1 minus E2. Which is also the hyperplane orthogonal to E2 minus E1. Okay? So these three white lines form what I was calling the braid arrangement earlier. And now the braid arrangement is really living in this two-dimensional space of V here. So let me do the general case of Sn. Is there any questions about this? You can sort of imagine that for any dihedral group, you're going to get a similar looking picture, just with more roots and more hyperplanes, but it sort of goes around, looks like that. So let's say W is Sn. Again, okay, so V is going to be this. Just as before. So in this case, what are the what are the roots? The roots will be Phi will be the set of all vectors of the form EI minus EJ, where 1 is less than or equal to I, and J, they're less than or equal to N. So I and J are just two numbers between 1 and N, but they're not the same. Okay. And this is essentially because, remember we said that alpha sub I was, so I guess I don't have it anymore, but alpha sub I was just EI minus EI plus 1. And the action of W, this metric group on this vector space, is just to permute the coordinates. So the things that I can get by taking EI minus EI plus 1, maybe I should say this. So it's because if I apply W to the vector EI minus EI plus 1, this is just going to be E sub W of I minus E sub W of I plus 1. And so the point is, these are exactly the vectors that I can get by taking something of the form EI minus EI plus 1 and changing I to W of I and I plus 1 to W of I plus 1 for some permutations. And so, okay, what are the positive roots and the negative roots here? Well, phi plus is going to be the set of EI minus EJ, where I is less than J. And phi minus will be the negatives of these. So phi minus is just the set of EJ minus EI, with I less than J. Okay? This is just because, well, you can see that if I want to write this, like EI might, so it's kind of like this, right? If I want to write E1 minus E3 as a non-negative, or as a linear combination of alpha 1 and alpha 2, I just have to do alpha 1 plus alpha 2. And then, like, similarly, the negative roots over here. So, in general, is this clear? Is there any confusion about this? Okay, so these are the positive roots and the negative roots. And I can think of the dual space So what is the dual space? It should be the set of linear functionals on this space. So I can think of this as like linear functionals on Rn that should send, well, okay, let me just write it. So I think I should think of V star as Rn modulo the span of the all ones vector. This sort of corresponds to the fact that I wanted the sum here to be 0. Right, so I guess maybe I can write this out more explicitly. So where, if I take something in here, let's call it x1 through xn, think of this as a linear functional that I want to apply to a vector gamma 1 through gamma n. Well, this is basically going to be the dot product. So I just take x1 gamma 1 plus dot 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 plus x in gamma n. And the point is that if the sum of the gammas is 0, that should tell me that when if x1 through xn was the all ones vector, for example, then this would just be the sum of the gammas, which is 0. Or more generally, if I take anything in the span of the all ones vector to be this thing here, like if all of the x's are the same, this is going to be 0. So that's why I really want to mod out by the span of the all ones vector, so that this really is like the dual space. And so in this formulation, if I want to look at the hyperplane orthogonal to EI minus EJ, this should be the set of all x1 through xn in V star. So I'm thinking of this as like a vector in this quotient space, such that xi equals xj. Because saying xi equals xj tells me that if I apply this to EI minus EJ, well, what is that going to give me? Right? If I take this vector x1 through xn and I apply it to EI minus EJ with this formula, that should just give me xi minus xj. And so I want to say, when is xi minus xj equal to 0? Because of this. Well, xi minus xj equals 0 is the same as saying xi equals xj. And so this is what I was writing down as the braid arrangement before. I said the braid arrangement is basically all of these hyperplanes in this quotient space, given by setting two coordinates equal to each other. Let me do one other example. So let's say W is the hyperoctahedral group Bn. In this case, I'll just identify V with Rn. And I'll so remember Bn has this Coxeter graph. So here's S0, S1, S2, dot, 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 Sn minus 1. This edge is labeled by a 4. And I'm going to let alpha sub Si, which I'll also call alpha I in this case. This will be EI minus EI plus 1. If I is between 1 and n minus 1. and I'll let alpha S0, which I'll just call alpha 0, this will be just E1. Okay. In this case, the set of roots, the root system, ends up being the set of all vectors of the form plus or minus EJ, or sorry, plus or minus EI, plus or minus EJ, such that 1 is less than or equal to I is less than J is less than or equal to N. But also these vectors, plus or minus EI for 1 less than or equal to I less than or equal to N. Phi plus is the set of these vectors where there's a plus sign here. Together with the set of these vectors with a plus sign. And phi minus is the set of things with a minus sign here. And things with a minus sign here. Okay. And if I identify V star with Rn, so I'll think of V star as Rn, where I do the same kind of thing as before. So I say x1 through xn applied to gamma 1 through gamma n is basically the dot product. Then the hyperplane orthogonal to EI minus EJ is just going to be the set, well, okay, it's the hyperplane where xi equals xj, just as before. Right, so this is the same reasoning as we had for the symmetric group. Now we also have H sub EI plus EJ, so this is now a root. And this is going to be the set of all vectors x1 through xn, such that, well, what does it mean? What does it mean for x1 through xn applied to EI plus EJ to be 0? Well, if I apply this to EI plus EJ, I just get xi plus xj. And so to say that that's 0 is just saying xi is negative xj. And then finally, H sub EI is just going to be the set of x1 through xn. Such that xi is 0. Okay? Yes, Kathy?
So in your example, your hyperplanes split your space into 6 regions, and 6
Yes.
is the order of S3.
Yes.
Does this generalize?
Yes, that is what I have coming up next. Yeah. So, let's define a region of the Coxeter arrangement. Coxeter arrangement again is the script HW. This is the closure of a connected component of the complement. It's the closure of a connected component of what I get by taking this dual space, V star, which is where the Coxeter arrangement is living, and I just delete all of the hyperplanes in the Coxeter arrangement. Union over beta in V, in V of H beta. Right, so as Catherine was saying in this picture, this is, well, I've overlaid V with V star, but if you only pay attention to the white lines, those are living in V star. If I delete those 3 lines, it breaks my space up into these 6 regions. So for example, like this would be one of the regions. Okay. I'm going to fix a specific region that I'll call the base region. So let's call it like math BBB. This will be the set of P and V star such that P of alpha S is greater than or equal to 0 for all S and S. And this will be called the base region. So in this picture, I want to say that, so what does it mean to say that P of alpha S1 is greater than or equal to 0? Well, this, okay, where is it? This is alpha 1. This is the hyperplane orthogonal to it. And this side is where, this is the set of, so this half space is the set of linear functionals that evaluate to something non-negative on alpha 1. And I know it's this side because, like, well, okay, I guess it depends on how you overlay them, but I'll say it's that side. Okay, so this would be the set of linear functionals where it sends alpha S1 to something non-negative. And then similarly for alpha S2, that would be this. So if I intersect them, I get this. So this region here is my base region B. Okay. And what we're going to see, maybe I'll start saying this, is that there's a way of identifying the elements of the Coxeter group with some of the regions in this arrangement, or of this arrangement. Okay, so there is an action of W on V star satisfying W of P comma beta equals P comma W inverse of beta. For all linear functionals P and, well, all vectors beta in V, and all elements W of the Coxeter. And this is going to define my action, because if I say, okay, well, how do I compute what W of P is? Like if I have my linear functional P and I want to say, what is W of P? Oh, maybe I should have not written parentheses. Okay, so what is WP? Well, I want to know, if I want to know what WP is as a linear functional, I want to know what does it do to a vector. So I want to know what does it do to beta. And I can compute that by saying, well, if I already know what P is, and I know W and beta, I just compute this. Right, so if I'm given P and W and beta, I can compute this already because I have the action of W inverse on beta, and then that tells me how to define WP applied to beta. Okay? And this will induce an action of W, the group W, on the set of regions of the Coxeter arrangement. Basically, by just applying this action to all of the things in the region, it will send that region to some other region. And this action is free. I'll remind you what this means. So remember, this means that for any region, I don't know what to call the region, let's say R. Maybe R is okay. For any region R, the only element of the group that fixes this region is just the identity element. Any other element will move it somewhere to some other region. And I guess the last thing I'll say is that this will allow us to identify elements of the Coxeter group with regions by just saying, so I guess I'll just write, we can identify some element W with the region W applied to the base region. So in particular, we're identifying the identity element with just the base region. So I would identify this region with E, and then the other regions would be identified with other elements of the Coxeter group. And I think I'll say more about this next time, but that's all.